You have any questions? Yes?
When would the midterm be?
Midterm, typically maybe after lecture 10. This is not final say, but it's always around lecture 10.
And will final be inclusive?
No, the final will be just for the part after the midterm. And it will be, I mean, we're going to do it. Thank you guys. Anybody want to drop? Or done? It's too late, yeah. Yeah, I gave you advice at the beginning, but you didn't listen. So let's continue with our rigid body kinematics. This is what we started last time. So we had what? The representation. How to represent the rigid body kinematics. Simply, we're talking how you're going to write R, the rotation matrix, right? The rigid body kinematics is intrinsically described by the rotation matrix R. How you're going to write R? The first description or representation was simply the direct one, using the direct entities or the entries of the matrix R. So R itself is a function of 9 angles, 9 entries, right? Alpha 1, 1 up to alpha 3, 3. This is 9 entries. This is one representation that we discussed last time. For this description, what was the meat, which is the kinematic differential equation? By the kinematic differential equation, I mean how R dot gonna evolve as a function of the angular velocity. R represents an angular position in one way or another, and I'm given the angular velocity and I need to integrate that. Or how the angular velocity dictate the rate of change of the angles, right? If you're using the direct representation, this is the differential equation we derived. R dot is simply negative omega tilde times R. Omega tilde is a matrix, R is a matrix, multiply both together you get a matrix. Each entry represents the rate of change of one of the entries of R. And this was, like you see here, we are representing R by 9 variables, right? Subject to 6 constraints, if you remember. And luckily, there are no singularities. Okay? Any question about that? Then we introduced Euler angles. So in in the language of Euler angles, R is a function of what? Anybody remember?
3 rotations.
Exact 3 angles, just 3 variables. So maybe phi, theta, psi, the 3 Euler angles, right? And then we need to know how these Euler angles evolve with time. This is what we derived last time, and you actually derived another form of it in a quiz. You did it right away. We derived an equation similar to this, right? Omega 1, omega 2, omega 3. So the interchange of the Euler angles is just linear function of the omegas. You exactly derive the other equation. Omegas as function of phi dot theta dot epsilon, which we can invert. And you can see here how many variables that. This is 3 variables subject to no constraints, right? Luckily. Very convenient. But there are singularities. This matrix, this was the inverse of another matrix, right? So we're dividing by something, and this thing can be 0 when theta equals 90 degrees, for example. There are singularities. Okay? Today we're going to talk about something else called Euler, standard Euler, principal axis. We're going to fill this today. The 4th column, which we will not discuss in this course, is the Quaternion. So particularly in spacecraft dynamics and sometimes in robotics, they use the Quaternion representation. Then you write R in terms of 4 variables, they call the Quaternion variables, Q1 up to Q4. So your kinematic differential equation, just tell me please how these Q's evolve as function of omega, right? The omegas, very similar to this equation. And now we have 4 variables, actually subject to 1 constraint, right? At the end of the day, we have 3 rotations. 4 variables subject to 1 constraint, simply the magnitude of these guys is equal to 1. Q1 squared, Q2 squared, Q3 squared, Q4 squared equals 1. And there are no singularities. Whenever we have redundancy, there are no singularities. And whenever you just use 3 variables, you will always have singularities. Okay? Any question about that? So we will not discuss the quaternion in this course, but we discussed these three things in detail. In particular, this guy will discuss it now. Any question? What is Euler's principal axis theorem? Euler, the same Euler, principal axis theorem. It's a theorem, it's proved. What's that? It says that, okay, here is your inertial frame, maybe N1, N2, N3. I don't care how complicated the maneuver performed by the body. At any instant, this very complicated maneuver, 3-dimensional rotation, is simply about a single axis. It's a single rotation instantaneously at each instant. Instantaneously, it's a single rotation about some axis. So this is the angular velocity omega, of course, about that axis. And we're going to call this axis the principal axis. So here is a unit vector in its direction. Okay? So the hypothesis of Euler says that I'm going to represent my rotation by a single rotational displacement like vector. It's an angle, single angle, just maybe 30 degrees, 40 degrees, about some axis. Okay? The magnitude is an angle, of course, in the direction of the instantaneous rotation axis. Okay? By definition, this means gamma dot equals what? By definition. Gamma dot equals what? Any suggestion? Come on, guys. What do we mean by gamma here? What do you mean by gamma here? What's that? What's gamma? Yeah, suggestion. I mean, we didn't talk about it before, right? So, no shame if you suggest an exorbitantly flawed thing. That's okay. What's gamma?
Just an angle about
That's an angle, right? So what's gamma dot by definition? Should be the angular velocity. So this is the vector representing my angular rotation. So by definition, gamma dot should exactly equal omega for sure. Right? This is by definition. Any question about that? So far, this is a hypothesis. So how we can know that this is really true? Let's see. If your statement is true, then this means that the rotation matrix multiplied by E, this is the direction of the axis of rotation. Okay, so we are rotating about E. And I'm multiplying E by the rotation matrix. So it should rotate E, correct? Anybody can guess what can we get out of that? If you rotate E about itself, what do you get? For sure I will get E. Again, if I have an axis like this, okay, in the old frame it has some components. Now I'm rotating about this axis, so in the new frame it has the exact same components because nothing happened to it, right? I'm rotating about it. The motion is about this axis, so it remains the same in the two frames. Okay? Anybody is not convinced by this? Anybody wants more illustration? Anybody doesn't believe this red statement? That when you multiply the rotation matrix, which is a rotation matrix about the axis E, we multiply this by the components of E, get the exact same components again. Anybody doesn't believe this? Okay, so if you believe it, now look at this. A matrix multiplied a vector gives you the same vector, or in general, a value, which is 1 here, times a vector. What's this for? What's this for? Matrix multiplying a vector gives you a value times the same vector. What's that?
Scalar of the same.
In general, when you multiply a matrix by a vector, it deforms it. Stretch it and rotate it and does everything. We're saying you multiply a matrix by a vector, it does nothing but just scale all the components of this vector by the same value. This is an eigenvalue problem. This is the definition of an eigenvalue problem. Okay? And you can see why we just make a big deal of the eigenvalue problem, because it's really interesting. If you have a matrix multiplying a vector, this is a very complicated operation on the vector. We're saying, no, for particular values, this is simply multiplying the value times the vector. Okay? So this is not true for anything, for any value, but for specific values, we call these eigenvalues, right? So if I look at this, what do you infer from this statement, red statement?
R are the eigenvector.
That E is an eigenvector for R, corresponding to eigenvalue, how much? 1, right? I have 1 here multiplying this guy. Okay, so if Euler's hypothesis is true, then this must be true, which means that any rotation matrix, we're talking about any rotation matrix must have an eigenvalue 1. And if this is the case, then the corresponding eigenvector will be the axis of rotation. Okay? So this was the theorem, actually, that Euler's proved. He proved that any rotation matrix has an eigenvalue 1. So this is indeed true. Okay? We'll not go through the proof, you can find it in the book. Any question about this? So give me any rotation matrix, one from before using Euler Angles or whatever, I don't care. Give me any rotation matrix. If you go to MATLAB and type I of this rotation matrix R, for sure one of these eigenvalues will be 1. And if you take the corresponding eigenvector, you know in MATLAB you can write V and D, right? This will be diagonal matrix having the eigenvalues over the diagonal, right? And V is a matrix, each column is an eigenvector. So if you take the corresponding eigenvector to the eigenvalue 1, this represents the components of the rotation of the axis of rotation, E. Okay? Any question about that? Any question? Yeah, this is new stuff, right? Of course, we didn't take it in undergrad and we didn't discuss it before. If you have any question, no shame at all. So bring it up, please. For your own sake and for the sake of the group. We're giving them, yeah, please.
So you're saying one of the eigenvalues you want. So
Yes.
because the rotation matrix has multiple different eigenvalues.
Yeah, it's a 3 by 3 matrix. It has 3 eigenvalues.
Okay.
So for sure, at least one of them will be 1.
Okay.
Its identity, well, just at the beginning there is no rotation. This is the special case where the 3 eigenvalues will be 1. But if you do any non-trivial rotation, then the other eigenvalues will be anything, but you have one of them will always be 1. And the corresponding eigenvector represents the components of the axis of rotation. This is very interesting.
So why is that? Why is that? If we have any rotation about something, then one of the eigenvalue will be 1.
Yeah, this is the theorem. Is that, yeah, this is why it's a non-trivial theorem to prove, and this is why Euler, when he did it, it's becoming a thing, right?
So you mean every rotation matrix?
Any rotation matrix, you can construct any rotation
It
matrix
has
you
one.
like. Whether it's about a single axis, whether you do 3 successive rotations and
Anything.
multiply them together to get 9 non-zero entries, they're very non-trivial, then just plug it in MATLAB and get the eigenvalues, for sure one of them will be 1. Okay, this is a big thing, right? And we're saying that the corresponding eigen, not only that, the corresponding eigenvector simply represents the axis of rotation. Okay? Okay. So this is the principle or the concept of Euler's principal axis. This is what we call the principal axis, about which rotation occurs. That's perfectly fine, but at the end of the day, please tell me how you're going to represent your rotation matrix and how these parameters will evolve with time, right? These are the 2 imperative questions that we always try to address. Okay, so if we aim to get a kinematic differential equation kind of thing, or even the representation, let us write this. So we have gamma dot equals omega. Here is gamma dot. It's simply phi dot in the E, right?